This is a video covering this stupid little problem I put up recently on FaceB. I haven't actually figured it out yet, but I kind of know how I would do it. I can't remember where I stumbled across this one. I kind of forgotten, but yeah, let's take a look at it. So, what is the shaded? Well, when you look at this, obviously you have a square, and then you have some circles, and then you have like intersections of circles, and you have some kind of difference of the intersection of those circles, and kind of making sense of all of that is well, it could be fiddly, right? When I first looked at this problem, I was really tempted to just kind of dive in and then pick it all apart by putting kind of lines and lengths and angles all over the place, and you can make it really, really ugly doing it that way, but you kind of lose the symmetry. Like, things you can do, you can chop this in half, and you have like 5 here, and then you do dashed line along there, and you can obviously find that coordinate's pretty obvious. It's 5 5 because it's the intersection of two semicircles of radius 5. What else can we do? This guy's going to be a radius of 10, so this point is definitely going to be a distance of 10 away from that point, and that might be useful if you want to find some other coordinates. You can spend a lot of time doing this kind of thing, and you end up making a great big mess. Yeah, so like I said, initially when I first did this, that was kind of my initial approach, just to like draw lots of lines and figure the coordinates, and then do it as the difference of shapes. So you can do like a line down here, and then you have like you have 2 segments. So if there's segments, you're kind of halfway there, and then all that remains is you can do like a line down here maybe, and you have you have another segment. But yeah, it gets messy. Basically, it depends on the kind of foresight you have into this problem. You can easily make things pretty horrible for yourself. And I guess like what I really wanted to try and tease out of some people, perhaps, or perhaps not, was how to see kind of the greatest symmetry here, because it does require, I guess, some affinity with like the 2D shapes which compose this this construction. So anyway, let's get rid of that, and let's try and see a better way of looking at this. And yeah, so I mean, if you've ever studied a little bit of maths, you may have studied shapes, and obviously, you have things like a circle, and that has a very specific definition in that it's a set of points which are all kind of equidistant away from the center. And then you start breaking this circle down, right? You can put like a line here, perhaps, and a line here, and all of a sudden you have this kind of funny shape here, and that shape is actually what we refer to as a sector. And it's pretty easy to calculate things like the area and the angle and how they will relate in that. And I think I'll go through that just to like build this video up from the ground up, just to show you how it all ties together. Because I know people who are watching this might be from kind of different backgrounds, and that can be quite challenging trying to teach people of different abilities and different backgrounds. But I'm going to try and make this as accessible as possible. So I'm just going to go over everything and see what happens. So anyway, these funny pie shapes, they're called sectors, and I'll go over some of the maths of that as well. I guess another thing we're going to need to know here is something called a segment. So when you have a sector like this, and then you put a line across here, and then this little sliver is called a segment. And I mean, this is terminology you might have learned if you remember your GCSE maths. I don't think they do segments in GCSE, but they definitely do sectors. And yeah, that has some area related to the angle here, which I'll go over at some point as well. So we have sectors and we have segments, which you can quite clearly see here. Right? I guess the semicircle is itself a sector, and the intersections of points is going to be considered segments. So yeah, that might be useful going forwards here. But there's another shape which I guess maybe isn't so well known, perhaps, like not in not in like the typical kind of standard syllabus, and that's called the, well, I guess it is, right? And that's the lens. When you take two circles, and they don't have to necessarily be the same radius, but when you intersect them, you get what we call a lens, right? A convex lens. This is a lens, right? And you can imagine the things which, the numbers which would characterize this picture, namely the radius of one circle, if you call that little r, and then the radius of another circle, if you call that big R, and then the distance in between them, I guess, would also be a pretty important feature. So if you know those three numbers, you pretty much know what lens you're dealing with. And I haven't actually done the maths of that yet. I'm going to try and figure it out just off the hand in this video, but that shape there is actually very, very important, with regards to solving this problem, because ultimately the red area is the difference of two lenses when you really look at it. So, and that's kind of what I was talking about with regards to like try to see the bigger picture, like even if there's also sorts of specific details to it, so you kind of have to abstract away the important features, I suppose. And the important feature here is that we have two lenses being kind of subtracted against one another. I know there are other ways of doing this, but I think this is definitely the most elegant. So here's one lens. So you can see that it's the intersection of the larger circle of diameter of radius 10, and then with a radius 5. That intersection is going to produce some kind of funny lens shape. And we also have this shape here as well. That one there. That is another lens, right? And what I want to do is find the area of those two lenses, and then naturally kind of subtract them against one another. Like I said, I haven't gone into the maths of finding the areas of lenses yet. I think I might do that ahead of time, actually, in hindsight, because I realize there's going to be different ways of characterizing this situation with regards to like the little radius, the large radius, and the distance. That that might produce some ugly maths using those numbers. And I don't want to use ugly maths. I want to use as elegant maths as possible. So I think I'm going to do a forward pass. I'm just going to stop the video here and kind of make sure this produces something nice that we can work with, because I don't want to waste your time. So I'll pause here and I'll come back in a second. So picking up where I left off, I can't quite remember where I left off at. But I'm pretty sure what I've got so far is looking good. I'm just going to take some time to explain it to whoever cares to view this video. This does require some, I guess, good knowledge of the GCSE and A level 2D shapes you typically draw, but I can brush over the main ideas if you want. So, again, the major insight between this problem is recognizing that we do have the difference of two lenses, and a lens itself is actually the intersection of two circles. So that's kind of the mind-boggling thing. We have a lens, intersection of two circles, and then we're doing the difference of two lenses. So all that really remains is to kind of figure out how to calculate the area of these lenses and then minus them against one another. And that's what I've gone ahead and done. I didn't use the whole X distance to actually calculate things in the end, but let's go ahead and see what happened here. So I kind of drew this picture out, and admittedly, I made a bit of a mess. I didn't make much progress here. I was trying to do, so you can see I've got the radius big R to one circle, and then the radius little r to another circle, and then I got the distance little x between them, and then I introduced this angle theta, and I realized, hey, you either need the little x or the little theta. You don't need both, right? So, and I was, I guess I was, we're trying to find this this lens, and the lens, I guess you can think of it as the addition of two segments. Again, a segment being, a segment being this kind of funny shape there. When you have a lens, ultimately you have two segments. 'Cause, if you had another circle like this, then you would have the addition of two segments. So if you can add up the two segments, then you have the area of the lens. And the area of segment, how do you do that? Well, you need to know a few things. So let's start off with a sector. Just quick reminder. Sector, if you have an angle theta and you have a radius r, then you can take this angle theta and you can divide it by the total angle, which is 2 pi when you're working in radians. Then you times it by the pi r squared. The pi's cancel and you get this nice little formula, a half theta r squared for the area of a sector. So that's A-level stuff if you ever did A-level maths. And then actually you got this segment, this little guy here. How do you get that guy? Well, that you can see how this segment is kind of the sector minus the triangle. So we need to know how to get the triangle, and there's a little formula for triangles. I'm not going to prove this one. I'm just going to state it. So if you have A, B, and then a big C, then the formula is a half AB sine C for the area of a triangle. So in our case, that's going to be the R times the R, which is R squared times by half, and then times by the sine theta. So this whole triangle here gives you the half R squared sine theta. Right, and then if you do the sector minus the triangle, you get the segment, and that leaves us with the segment formula. Let's just write that out. So what we're doing now is this guy minus that guy, and you can see how the half and the r squared factor there, and you get this nice little formula, a half r squared theta minus sine theta. So again, that's kind of A-level stuff. That's the formula for this segment. Now, if you can add 2 segments up, you could go with the lens, all right? But so let's take a look where I got to. I did try having a bash at that. I made a bit of a mess there, so I'm going to move over to the other page and kind of explain what I did. Yeah, this was my less messy page. All right, let's take a look at construction. So here it is. All right, a couple of lens, a couple of circles. I got the angle theta there, and then the angle phi. I introduced the x there, but honestly, I didn't end up using that distance at all in the end. I just ended up focusing on the angles because that turned out to be a nicer way of doing things. And then I was just working off of that. So I had the little white area there, which is kind of a segment in its own right, and that's going to be given by so that's the radius r squared, and then that's using the segment formula with the angle theta and the side length big R. That's that segment formula there, the white area. And then I had this little green area, so I was basically doing it in bits. And then the green area, well, that green area you can do is the larger triangle minus the left triangle, which is what I called it. So the larger triangle, that's the R by that length, is going to be the half r squared sine theta, again using that triangle formula. And then the left triangle, that was kind of this little shape here, that's going to be the half r squared and then sine theta cos theta. So that length there is going to be r cos theta, and this length is going to be r sine theta. Times them together. This is a right angle because I was just the line between the centers is going to split. It's going to be right angle to the line between this vertex and this vertex. So you can just take that side, and you can take the r cos theta side, the r sine theta side, times them together, and then times by half, and that gives you the left triangle. And when you minus those against one another, you get left with the green triangle, which is this formula here, right? And then what I want to do is I want to do the white plus the green. So that's going to be adding this formula with this formula, and you can see I have I got minus sine theta here and plus sine theta here. Those terms actually cancel, and you just get left with the theta and then minus this cos theta sine theta term, and that's what this term here is. So that's the white plus the green, and then you want to double that up to give you the entire right segment. That's what I use the purple for, so or whatever color that is. It's going to be equal to this guy. And then you can take that and reason by symmetry that the left segment is going to have exactly the same formula, just with all the r's and the big r is going to become little r, and the theta is going to become phi in the formulas. and then naturally when you add those up, you get the total lens, which gives me this equation for the entire lens, just in terms of the two angles and the radii, which I kind of thought was a good way of stopping right there. I mean, I know there's going to be other ways of writing that, but I kind of just wanted to roll with that and see if it's going to produce something useful. And it did. It was quite nice in the end. So that's my total lens equation. And then it just boils down to, well, finding the radii as well as the angles that are required to find the lenses here. So yeah, so we have this smaller lens here. This one's actually quite easy to get. So looking at the formula for my lens, you can see how it involved the two radii as well as the angles theta and phi, and it gave me this funny thing. So let me paste that over just here. Right. There it is. And I'm basically, just applying that here with the smaller, the white lens, as it were. So the angles here are pretty trivial because this is smack bang in the middle. Because you have a radius 5 and a radius 5, they're going to intersect in the middle. So this angle here is going to be pi on 2, and this angle here is going to be pi on 2. So applying this formula is dead easy. And both of the radii are going to be 5. So when you add these up, you just get the same thing twice over. So where did that leave me? It left me the 5 squared pi on 2 minus what was my reasoning there? Left lens. Oh yeah, I was thinking about that as yes, I see. I didn't actually use this formula when I was doing that. Don't lie. All right, let me delete that. I don't want to use that. Where this came from, I was just thinking about it as two segments. So I you have a line down there, and this segment here. Well, we kind of know everything we need to know. We know it's a radius of 5. We know it's a pi on 2. So again, you can use that segment formula, which, just to remind, it was the half r squared and then theta minus sine theta. That's the segment formula. And you can use that to get that segment there. And that's going to be the half 5 squared and then pi on 2 minus sine pi on 2. That's what I have here. But obviously, both the segments here are going to be identical because both the radii are 5 and both the angles are pi on 2. So this becomes quite trivial to find the lens. I didn't actually use the lens equation for that one. I just used, doubling up the segment formula there. And that gave me this left lens expression, 25 pi on 2 minus 1. And then what else did I have? I had yes, the larger lens. This one's a bit more fiddly, but it's not too bad if you just take the time to think carefully about it. So I've gone ahead and drawn the two angles we need, the theta 1 and the phi 1. I should have just called them theta and phi, but there you go. And you can reason as follows. So I know this is a radius of 10. So in this formula here, up here, the theta would be this guy, and the radius would be that 10, if you remember where that formula came from. And this phi would be this guy, and that little r would be this 5, right? So you have to appreciate that's how we're going to use this formula. And then it remains to just find expressions for, well, the theta as well as the phi. And also, the sine of those angles as well, which again is actually relatively easy if you don't make too much of a mess here. So yeah, you can reason as follows. We know this is a radius of 10, that circle there. We know this is a radius of 5. So if you put a dashed line down there, then you know that's going to be 10. You know it's going to be 5. So because it's a right angle, right? And then this is going to be the root 10 squared plus 5 squared is going to be root 125 by Pythagoras. And then you can reason that this triangle here is also right angled because we know that that squared plus that squared is going to be that squared, and therefore that triangle is right angled. So this is, this is definitely going to be a right angle right here, which again makes things much nicer for us so far as finding nice expressions for those angles. And then right. So in here you want the r squared to be the 10 squared, and then you want the theta. Well, I just took advantage of the 5 and the 10 here because this is a right angle triangle now, so you can just do tan inverse of 5 on 10 is going to be tan inverse of a half, and that was where that's coming from, the tan inverse of 5 on 10, because it is just a right angle triangle. And then likewise, this sine theta times cos theta, that's going to be cos theta is 10 on root 125 and sine theta is 5 on root 125. So when you times them together, you get 5 times 10 is 50. And then you get the 125 on bottom. That's where that's coming from. And it's the same on the other side, right? You got the 5 squared there. And then you got the tan inverse of the 2. Again, that's coming from the phi. This angle here is going to be tan inverse of 10 on 5, which is tan inverse 2. And then again, minus the sine phi cos phi, which actually turns out to, when you times them together, you get the same thing because cos phi is 5 on root 125 and sine phi is 10 on root 125, and you times them together and you get the 50 on 125. And then I did a few other things. So tan inverse of a half, this is something to worth, which I kind of noticed, right? So tan inverse of a half in addition with tan inverse of 2 is going to be equal to just pi on 2. And that's basically saying that angle plus that angle is pi on 2, which is 90 degrees. So I took advantage of that here. So you have 25 tan inverse 2 plus 100 tan inverse half here. So when 25 of those are going to get added together to give you just 25 lots of the pi on 2, right? And then you're going to have the remaining 75 from the 100 there, tan inverse a half, and then you got and then you can see how you get the 10 squared. The 10 squared, lots of this guy, and you get the 5 squared, lots of this guy. That gives you 125 lots of this guy, but that cancels the 125 on the bottom, so you just get minus 50 coming out the end. All right, and that gives you expression for the larger lens. The larger lens is this entire thing here. That's the larger lens. And then all that remains is to do the larger lens minus the smaller lens, and we're good to go. Now, here's the smaller lens. Reminder, this was the expression 25 pi on 2. So when you minus them, this term here is going to cancel, right? That guy gets knocked out with that guy. And then you're minusing the left lens, so you get minus 25, which is going to be plus 25. So you get minus 50 plus 25 gives you minus 25, and that gives you this final expression here. This is my final expression for the, for the red area. This 75 tan inverse half minus 25. So, funnily enough, it didn't actually involve pi. I was kind of expecting it to be some fractional multiple of pi, but there you go. And when you plug that in your calculator, it's really important you're working in radians here, because that segment formula I mentioned only works when you're using radians. When you plug that in your calculator, that gives you the 9.77. So you can think of that as a percentage of the entire square, because the entire square is 10 by 10, which is 100. So you can think of this as like 9.77% of the square. So there we go, right? And, when I got to that point, I was like, there's a really good chance I made a massive mistake doing that. So I've actually gone ahead and used some tricks with Photoshop and Illustrator to kind of check this. So here's like a little Illustrator file I made. I just got rid of the borders, and then I kind of exported this as a PNG. And then I went over to Photoshop here, and you can see in one screen I've kind of selected all the red pixels. I just did this using the color range command, and it tells us 4963 pixels over here. Obviously not perfect. You can see it's kind of missing a few, right? So it's going to be a slight underestimate, something worth mentioning. And then when you get rid of all the pixels and you just deselect them, you get this many pixels. You get 51,076. So I just took the division of those, and you can see it's given me something which is pretty damn close to my answer. So 0.972. which is about 9.72%, which is very close. Again, it's slightly below. I was kind of expecting that to my 9.77% answer here. So yeah, I'm pretty confident what I did there was, working pretty nice. So, there you go. That's a bit of maths if you like maths or not. Anyways, hope you had fun. I will maybe see you in the real world sometime. Who knows?